Greetings all. I'm down in the bowels of our house, so-called basement, in my man cave, which is really the edge of the children's playroom. Not too many man caves have Monopoly, Clue, Checkers, Yahtzee, Uno, Sorry, Dead End Drive, as well as playhouses. But you do the best you can. We're going to be looking at the Work Energy Theorem, and my goal is to set up as many problems as I can in the next few minutes. And my upload speed for these things has been extremely slow, so hopefully this will be in place in time for your class in a few hours. We are on page 131, looking at the skier. And in example 5.4, the work energy theory says all of the kinetic energy and all the potential energy we have at the top must equal all the kinetic energy and potential energy we have at the bottom. So there's my kinetic plus my potential initial, and then that's got to equal it all at the bottom, final. Your textbook sets them up differently. Your textbook likes to approach these problems with the change in kinetic energy and the change in potential energy. So the way that I'm going to set up these problems is going to look different, just in case you think more along the lines that I do as opposed to the lines in the book. I like to think of how much energy does a system have at the very beginning and what happens to that energy along the way until you run out of energy. The law of conservation of energy. So in this case, obviously your kinetic energy at the very top, before she starts going down the slide, is zero. She's all potential. And then at the bottom, since she's at a zero height, her potential energy goes to zero, and all she has is kinetic. Now, of course, we can modify this problem. If indeed there was friction on the slope, then what we would say then is all of her potential energy is going to be converted into the energy to overcome friction, which is work. And work, you'll recall, is force times distance. So we'll have the force of friction times the distance down the plane. The distance down the plane. Please note that D here is the hypotenuse of the triangle, shaded in blue, not 10 meters. And of course, to do this problem, we would have to know one of these two terms, that one or that one. We could even make the problem more interesting if we said when she gets to the bottom, she starts to move horizontally. What's going to be the distance that she travels? In which case we'd have to again know the friction on the horizontal surface. Let me make some room here. The friction on the horizontal surface, and the distance, we'll call that x horizontally. Please note that your two frictions would be different. You would probably have a different coefficient of friction on the slope than you would have on the horizontal surface. Please also note that since your force of friction divided by the normal force equals mu, it's very common, especially on horizontal surfaces, to say that your force of friction equals mu times the normal force. And if you're on a horizontal surface, your normal force and your force of weight equal each other. So we can say mu equals the force of weight, which is mu equals mg. All right, let's move on to the next problem. And this problem is on page 134. I'm going to erase my scrolls. Probably an easier way to do that. Now in this example, again, you have all of your energy at the top, which is your potential energy, no kinetic energy. It all becomes kinetic energy at the moment of impact, 1/2 mv squared. And so this is very easy to find the velocity of the diver when the diver enters the water. We could also talk about what's going to happen when this person goes into the water. How far will they go? Well, all their potential energy will be converted into all kinetic energy just before impact, and assuming no energy lost to air friction, and all of that energy will be the energy it takes to plow through the water some depth d. And so here we would have to know the force of friction of the water. We could even modify the problem and say, what if the pool is so many meters deep? If that number is less than this, we are going to have to add a 1/2 mv squared in order to get the velocity of the diver when the diver hits the bottom of the pool under the water. And usually you try to avoid that. Or, as you've heard elsewhere, you hate it when that happens. Now let's move on to example 5.7 on page 135. And here they talk about a water slide, der Stuka, and why you would name a slide after a German dive bomber, excuse me, that wreaked so much havoc and destruction, I don't know. But be that as it may, since I'm half German, I'm going to have to go along with it. And in this problem, there's two parts. Determine the speed of the woman at the bottom of the slide, assuming no friction. And then if the woman is clocked at 18 meters per second at the bottom of the slide, find the work done on the woman by friction. So once again, you have all of her potential energy at the top, and all of that is going to be converted into kinetic energy at the bottom. And the first thing you know, of course, is that the mass of the woman is irrelevant. Now, if you're given a velocity at the bottom, and these two values do not equal each other, in other words, what we're saying is that all of her potential energy, all of her potential energy is going to be converted into two things. It's going to be converted into overcoming friction down the slide, so we have to have the force of friction times the distance or length of the slide. Let's use L for the length of the slide. And whatever energy is left over contributes to her velocity. So variations on this problem would be find her velocity given so much friction, or find this friction given a final velocity and a length of the slide. And hopefully you're beginning to see that this work energy theorem is a very, very convenient and easy way to work through problems that otherwise might seem extremely complicated. All right, let's go to the next problem. Problem 5.8. I better back up a page here. I'm looking at the computer while I'm doing this screencast, and the problem is when I download the textbook in order to look at it, like I project in class, it doesn't allow me to make notations on the pages. So, as you might gather, this is an inferior way of presenting this material, but it's the best I can do right now. And in this problem, that's right, this is the one that we already did, I think. So let's hit the ski slopes. Example 5.8. Once again, we have all of our potential energy at the beginning. We need to jazz this up a little bit. Let's go with some purple. This will be for Caitlin. And so we have our potential energy at the top, mgh. At the bottom of the slope, it has all become kinetic energy, 1/2 mv squared. You're probably noticing a pattern here. If there was friction on the slope, we would have to add the force of friction times the distance down the slope, which would be the hypotenuse of the triangle. It would be, you'd have the height there, and you'd have to use sine in order to find the hypotenuse. Then, of course, we could say, well, what if the friction is so great that the skier hits zero speed at the bottom, which kind of defeats the purpose of skiing? Well, then this whole term here would disappear, and all of her potential would be lost due to friction, his potential. That would be unlikely to have as a problem. We could also say now we're going to be moving along the surface, the horizontal surface, and we might want to talk about eventually coming to a halt. Well, if you're going to come to a halt horizontally, just like when you did the lab on the coefficient of friction and the angle of the floors downstairs, you would have to have the force of friction along the floor, and then the distance. The book's using the letter D here, so I'm going to change this to be, let's call it L for the length of the slope. So we have the height of the slope, the length of the slope, and the distance horizontally. You probably would have two different forces of friction, but once again, as soon as you're on a level surface, your normal force is going to equal the force of weight. Remember, this is not true if you're on an incline. It is only true on a horizontal surface. And so in which case your force of friction would equal mu times your force of weight, which would equal mu mg. And you might notice in this problem, especially if we were to expand this out the same way, the mass of the skier becomes irrelevant. It cancels out all the way across the problem. Now let's move on to another term that we can add to our work energy theorem, and that is the term spring potential energy. And here we're not talking about all the photosynthetic energy stored in plants getting ready to burst forth in a beautiful April morning. That's not the spring we're talking about. Here we're talking about a coil of metal that you can stretch or compress and store energy in it. Now, there are two equations when it comes to springs. F equals negative Ks, and work equals 1/2 Kx squared. And I need to fix this. There we go. Now, x is the distance that you compress or stretch the spring. or if it's an elastic band, that you stretch the elastic band. Now, of course, you can always stretch a spring or a band too far and exceed its elastic limit. So we're assuming we are doing reasonable forces to stretch the spring. And you can see that these two terms are proportional. The greater the distance x that you want to stretch the spring or compress it, the more force you need. So K becomes your proportionality constant, and that proportionality constant has the units of Newton per meter. Don't forget that. Easy way to lose a point on a test, not having the correct units of your spring constant. The other thing you should notice is the fact that we've got a negative sign right there. And that is because when let's say I compress the spring this way, the spring wants to push back. We call that the restoring force. And since it's sort of an equal and opposite kind of force, that's where we get the negative sign from. It's a restoring force. Now, your book derives this equation for you. And every year on the test over Chapter 5, students use this equation in one of the multiple choice problems instead of this equation in order to find the work done in compressing a spring. Don't you be the one to make that mistake. Remember, this is just force, and this is going to be the work done. And the reason it's not linear is because it takes more and more and more force to stretch the spring. It's not the same force all along. Every centimeter that you stretch the spring doesn't take the same amount of force. Early on, it's easy to stretch it, but as it gets stretched more and more, it takes more and more force to stretch it the same distance that you used to stretch it. And that's the derivation in your book, which I don't have time to go through right now. So, having said that, this right here is called Hooke's Law. Hooke's Law, named after Sir Robert Hooke, who discovered this relationship. He has an interesting history in science and some very important Christian beliefs as well. So now what I'm doing as I look at the book, and hopefully you're doing the same thing, here we are on page 138, and now we've expanded our work energy theorem to include changes in potential, changes in kinetic, and changes in spring energy, elastic energy. So if we're going to do a problem, and here we are. All right, someone's going to have to tell me how to make this disappear a lot faster. Just don't have time to experiment. Anyway, in this problem, we have a block on a horizontal surface. It's connected to a spring. We're going to push the block to the left, compressing the spring. Therefore, the force of friction will be going to the right, opposing the motion of the block. Notice that the weight vector and the normal force are equal and opposite. There's your vector diagram, your free body diagram. We're supposed to find the speed of the block when it first reaches the equilibrium point. The equilibrium point would be, in this case, x, where the spring is neither compressed nor stretched. Obviously, if you compressed or stretched the spring and then let the mass go, it would go back and forth, and let's see what this sounds like. Wah, 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 wah. Boing, 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 back and forth. There's your sound effects. And until it would eventually come to a halt because of friction. But the idea in number A is to find the speed of the block when it first reaches the equilibrium point. And so we can say that all of the energy that used to be stored in the spring, which would be 1/2 k x squared, where x is the distance that we stretched the spring and k is the value of your spring constant, all of that energy is converted into kinetic energy. So the block is moving fastest when it's going through the equilibrium point. And we would be able to calculate the velocity of the block. Now, in part B, it says find the speed when x equals half the distance that you stretched it. And so now we're going to say we still have some spring, some energy stored in our spring. Here, x is going to be 0.050 meters. And over here, my x is 0.025, half as much. The value of k, interestingly, doesn't change. It's constant throughout the problem. Then in part C, it says repeat A if friction acts on the block with a coefficient. So that means we're going to get rid of this part here, since we're repeating part A. And that means that all of my stored potential energy in the spring is going to do two things. It's going to show up as a speed of the block, but not until after it's lost some of its energy due to friction. So there would be my force of friction, and here would be that distance x, 0.050, along which the block was rubbing on the surface, the horizontal surface. So all of my energy, to start with, is used up in two places. Overcoming friction, and whatever's left contributes to the velocity of the block. All right, let's move on. And I think what I'm going to do here is stop this part and make it a smaller chunk and hopefully be able to get this uploaded so I can finish the chapter with another discussion.